We're going to talk about what happens to things when they're undergoing constant acceleration now. And things undergo constant acceleration all the time around us, provided air resistance is negligible, because that's what gravity does. It took a long time to realize that air resistance was an important feature of falling things. Aristotle used to think that heavy things just naturally fell faster than light things, which looks like a reasonably good result of that experiment. But it's not necessarily the heavy thing and the light thing are acting differently under gravity there, because he didn't think about air resistance. Galileo put forward a sort of a thought experiment that made Aristotle's idea that heavy things fall faster than light things seem a little strange. He said, suppose you have one cannonball and another cannonball exactly like it. All right? So because they're the same, they'll fall the same. Now, if we had a bigger cannonball instead, you'd expect that to fall faster, according to Aristotle, because of gravity. Suppose you have those two cannonballs, and instead of having one twice as big, we just had those two attached by a little chain, like just a tiny little hair. That's now a bigger thing, right? So when I drop it, it should fall faster. But we know that if we attach two cannonballs by a hair, that's not going to change how fast they fall at all. So that goes against our intuition. Oh, says Aristotle, okay, you have to make it thicker. They have to be properly attached, all right? Well, how thick does it have to be? Does it have to be just a rigid little chain? What if I put a tiny dob of glue between them? Do they suddenly fall faster now? That doesn't really work with our intuition either. And in fact, what we understand now is that air resistance is really important in understanding why heavy things seem to fall faster. If I have my piece of paper, then it falls. It's falling because of gravity, but it's also being pushed up by the air. And the main reason that this pen falls faster than this piece of paper is because of the air resistance. And you can test that by taking the air away. And then when you've got no air resistance, you see that these two things will in fact fall at the same rate.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So that's got to be absolutely the world's most expensive version of that experiment ever. And yet it wasn't even in HD. You can get the same effect just by putting things in a vacuum tube and sucking out the air. Now, Galileo didn't just think about gravity and say, I don't think Aristotle can be right. He actually went and did the experiment. And when he was doing the experiment, he didn't have really great clocks, and things fall pretty fast, so it's hard to get accurate time measurements. So he slowed things down by putting things on a slope and rolling them down the slope. And he tried different slopes, and he found that indeed gravity caused things to accelerate at a constant rate. So to keep things simple, we'll just start by considering motion in a single direction. So we have some object that's got a position we can define, and it's traveling in some direction. It's really important in your diagrams to be as clear as you possibly can. And so we're going to have a before diagram and an after diagram. And you'll note I've explicitly said after a time t for my diagram, so I've kind of defined my symbols in my diagram, and that's good practice. So after a time t, it's going to be somewhere else. Now, in order to figure out how it's going from one to the other, we need to know its acceleration, and we also need to know its velocity. Just because it started on the left, and so it started with a negative position, doesn't mean it was going to the left. It could have had an initial velocity where it was heading to the right. So let's look at the initial velocity. So the initial velocity is a vector. It's got a direction, so it's either positive or negative if we're going in one dimension. And we're going to call that u. So that's its initial velocity. And we're going to have a final velocity. And the final velocity could go in either direction. I'm just going to draw it to the right, assuming that it's going to be positive for the purposes of this diagram. And of course, the reason we're working all of this out is that we've got an acceleration. So after a time t of acceleration, and again, I'll direct that to the right, assuming the acceleration is in the positive x direction. Let's look at what happens graphically before we worry about the algebra. And so you have the acceleration doing nothing at all over time. So if I have time on one axis and acceleration on the other, we've already drawn on our diagram that it starts at a value of a, and it does not change. That's our idea. We're talking about constant acceleration. So it's like that. We've drawn it above the origin because our diagram has it as a positive number pointing to the right. Now what happens to velocity? Well, we know that the velocity is changing at a constant rate. So it starts at u at time t equals 0, and then is going to increase because our acceleration is in the positive direction. It's going to increase up until it gets to our final value of v. And that should be a lovely straight line. I've drawn a reasonably straight line. And of course, the slope of that straight line is exactly our acceleration a, which is a constant, because that's exactly the definition of the acceleration. It's the rate of change of velocity.